Alrighty, howdy folks. So right now let's look at chapter 12 and section 2. It's all about vectors. Quite possibly a lot of you already know about vectors. I mean, you must have had physics 1, physics 2, some of you probably are taking, or if you are mechanical or some civil, then you would have taken statics and you probably encountered vectors there too. But for the sake of completion, please allow me to talk about this. Maybe there's a point or two that you did not know that you will probably learn. Okay? All right. What's that American expression? Without much further ado. All right. Definition. Mathematicians always want to give proper definitions of things. A vector is a quantity with magnitude and a direction. As simple as that. What's a vector, man? Well, it's a quantity with magnitude and direction. That's how you define it, right? So the one way you can represent a vector is by using something like what I've shown here, an arrow. Now, there are two things about this arrow. One is the length of it itself, right? The longer it is, the greater is the magnitude. That's the idea. So the length of the vector is proportional to the magnitude of the vector. Put another way, suppose I have a vector that is twice as long as this one, then that means that vector has double the magnitude of this vector, simply because its length happens to be double the length of this one. Cool? And also the second thing is, which way is this arrow pointing? Well, the arrow is pointing sort of northeast direction. So that means the direction of the vector is in the northeast direction. So the arrowhead indicates the direction of the vector. So we know magnitude is the length and the direction is indicated by the arrow. Okay, that's what the length of vector is proportional to the magnitude and the action, blah blah blah. I got a question to ask you. Is vector A equal to vector B? What? Yeah, is vector A exactly equal to vector B? Uh, let's say the length is exactly the same, and they are both pointing in the same direction. In that case, would you say that these two vectors are exactly the same? Well, you might wonder, hey, this vector starting point is over here, whereas this vector starting point is somewhere else. So their starting points are different, and obviously their ending points are also different. So they cannot be the same. You would say that the vector is exactly the same if this falls right on top of it, right? If it has been moved. That's one thinking, one kind of thinking that we might employ. But that is wrong. That is wrong thinking. See, this is why definitions are important. What was my question? Is vector A equal to vector B? Immediately you should ask, what in the world is a vector? Oh, vector is a quantity that has both magnitude and a direction. Do these two vectors have the same magnitude? Meaning, do they have the same length? Yep, they have the same length. Are they pointing in the same direction, both of them? Yeah, they are. End of the story. They must be equal. But their starting points, we don't care about the starting points. You see, that's the idea. As long as two vectors have the same magnitude and direction, they are equal. Cool? All right. Note that in the above figure, A equals B, vector A equals vector B, since the two vectors have the same magnitude and direction. Oh, by the way, I need to mention, usually I want to use a vector, say to represent a vector A, I write a lowercase a and put an arrow on top of it. I like that way. It's less confusing. The reason I'm mentioning that is because in the textbook they use this stupid boldface letter. Apparently, the moment you see a boldface, you should understand they're talking about vector. But when you and I are writing, how in the world can we write bold-faced? How can we differentiate a regular letter from a bold-faced letter? We cannot. So I think that's a stupid idea to use boldface. Uh, so I'm going to use the A with a arrow on top of it to represent vector A. Okay. But when I give you homework and all that, please understand that the homework people, because it comes from the textbook people, they may represent a vector with a bold face. Okay, cool. Next, ooh, a long definition. Definition: if C is a scalar and V is a vector, then the scalar multiple CV. Okay, there's something called scalar multiple. C is a scalar. Uh, the term scalar has um, is a bit more complicated than in upper level courses. A scalar could come from any field and all that you should say. But in our case, when we say scalar, we simply mean a real number. Okay? C is a scalar, means C is a real number. If C is a real number and V is a vector, then the scalar multiple CV is also another vector whose length happens to be absolute value C times the length of that vector V. And direction is exactly the same as V if C happens to be greater than 0 and is opposite to V if C happens to be less than 0. I'll explain to you what all that means in just a second. Okay. And another important property is if C equal to 0 or V equals 0, the vector V itself is a 0 vector. Okay. What does it mean? What does it mean to say a 0 vector? A vector with 0 magnitude. Can the direction be 0? Hey, what's the direction of that vector, man? Oh, 0. That almost doesn't seem to make sense, right? Well, in a way, theta is equal to 0, which points along the x-axis. Maybe we could interpret that. But typically, a direction of 0 doesn't make sense, but a magnitude of 0 in case of a vector actually makes sense. So there is something called a 0 vector. Should I put a 0 on top of the, should I put an arrow on top of the 0? Uh, yeah, you're right. That would be better. But traditionally people don't put a 0 in. Based on the context, apparently we are supposed to figure out when I say vector v is equal to 0, a vector cannot equal scalar. The 0 is as such a scalar because it's a real number. So strictly speaking, I should not say vector v is equal to a scalar 0. I should put an arrow on top of it, but based on the context, you kind of understand. Okay. Um, However, here C equals 0. C is just a scalar, so this 0 is actually 0, a scalar 0. Then automatically CV will be 0. Okay, that's something that we need to understand. Now, what in the world do I mean by the scalar multiple CV and all that stuff? Okay, suppose we have a vector V whose magnitude and direction are as shown in this figure. Then what exactly can we say about this vector and this vector? Okay. Note, let's pick the second one. the direction is exactly the same as the direction of V. Are you with me? The two directions are exactly the same. But when it comes to the length of this vector, it is twice as big as V. So what should we call this vector? Well, according to the definition of scalar multiple, because this vector has double the magnitude of V, that is C equals 2, this vector is 2V, right? Mm, is that okay? It's, direction is the same. Magnitude happens to be twice this magnitude of V. So this is 2V. As simple as that. What's up with this one though? Is its magnitude the same as the magnitude of V? Yep, it is. But what is its direction then? Oh, it's exactly the opposite of V. So what should we call this vector? It's negative V. That's the idea. Or in other words, maybe I should ask you, is negative V a scalar multiple of V? Is 2V a scalar multiple of V? Yeah, of course, man. It's a scalar times a vector. Good. I agree. Is negative V a scalar multiple of V? Yes, it is. But there is no some constant times V, man. There is, man. Negative 1 times V, right? C, when I said is a scalar, that means it has to be a real number. Is negative 1 a real number? Yes, it is. So this is nothing but negative 1 times V. And according to this, what is CV? Is a vector whose length is absolute value C times. In this case, C happens to be negative 1. So what is the length of this vector? The negative V's vector? Oh, compared to V, take the absolute value of negative 1, which is 1. So 1 times the length of V. Oh, that means the magnitude of this vector is exactly the same as the magnitude of this vector V. Now, what else? If C is greater than 0, the direction is the same. But if and is opposite to V if C is less than 0. In our case, negative 1 is less than 0, and that's why it's pointing in the direction opposite of vector V. Cool? Alright, so basically we are applying the definition, and that's something I wish for you to learn. Apply definitions to figure things out. Okay, next. How do we add vectors? There are different methods, graphical methods and also analytical methods. Uh, One of the methods is what's called the triangle method. Okay, let me illustrate that. Not because you don't know, you probably already know this, you've done this in physics, but please bear with me. Let's say we have two vectors A and B like this. And what are we supposed to do? We're supposed to find A plus B, vector A plus vector B. How do we do that using this so-called triangle method? Well, first draw the first vector A, right? But A was here, man. How can you draw somewhere over there? Well, we already talked about this. This vector is exactly equal to that vector, even though they do not have the same starting point and ending point. They have the same magnitude and direction. That's why they are the same, right? Equivalence of vectors. Cool. After you draw the first vector A, then you draw vector B, but where you draw it is the important point. At the head of this arrow, you put the tail of B. Okay. What do? You put the tail of the second vector B where the head of the first vector A is and draw it. When you do that, from the tail of A to head of B, that would automatically be A plus B. Cool? I wonder why they call this the triangle method. Duh! Once we do this addition, we get a triangle, right? As simple as that. So this is the triangle method. Draw A first. Let me go back. Draw A first, and then at the head of A, put the tail of B and draw the vector B. And then join the tail of A with the head of B, and you got the triangle where the biggest that line that vector is A plus B. The resultant vector it's called. Cool. Now, what's that? A minus B. Yikes. Can you subtract a vector? If you can add vectors, can you subtract vectors? Of course you can. But how, man? Well, A minus B, can I think of this as A plus negative B? The moment I think of A minus B as A plus negative B, I'm in business. Oh, by the way, if we know B, do we know how negative B looks like? Well, it's exactly the same magnitude. Negative B would have the exact same magnitude as B, but the direction would be opposite. Right? So, to draw A minus B, we will draw A plus negative B. Again with the triangle method, how do you draw A plus negative B? First draw the vector A, and then at the head of A, put the tail of negative B, and then draw negative B. So that's what I did. Same magnitude as B, but direction is opposite, right? Pointing downward and to the left. And then, as before, join the tail of A with the head of negative B. Voila, you get A minus B. Cool? All right. This is another method. It's called parallelogram method. Again, we'll try to add vector A and vector B, A plus B. Let's try to figure that out. In this method, you do something slightly different. As the name itself indicates, we are going to construct a parallelogram. And how do we do that? Check this out. First, we draw A as before, like in the triangle method. But this time, we will draw vector B where the tail of B coincides with the tail of A, like that. Okay? So once we do these two vectors, now go to B, the head of B, and draw a line parallel to A. Okay? At the head of B, draw a line parallel to A. Okay? Like that. Similarly, go to the head of A, but this time draw a line parallel to vector B. Cool? The head of B, vector parallel to A. At head of A, vector parallel to B. Line parallel to B. And where they intersect, from the tail to the head, to the intersecting point, if you draw a vector, that's going to be your A plus B. Okay? I usually do triangle method. Right? This is how you add two vectors graphically. With that, let's move on to something called components of a vector. Now, if I have an XY coordinate system, I can locate a point whose coordinates are a1, comma a2, right? The x coordinate is a1, y coordinate is a2. How do we do that? Well, on the x-axis, go to an a1, a distance of a1, and similarly on the y-axis, go to a distance of a2. At a1, draw a vertical line. At a2, draw a horizontal line, and that's how you locate this point a1, a2. But then when you draw a vector going from the origin to this point, would you agree that is actually a vector going from origin to this point? Yeah, that is called vector a1, a2. Okay, now notice how the components are written. The a1 and a2 are called the components of this vector. We put this in this triangle brackets, angle brackets, not triangle, sorry, angled brackets. So enclosed in angled brackets, a1 and a2 indicate that the x component of this vector is a1 and y component is a2. Cool? So that's another way we'll represent vector using the components. Now, if this vector and this vector have exact same magnitude and direction, can we call this vector as a1, a2? Yeah, by that equivalence property that they have this that we talked about, they have the same magnitude and direction. So if this vector was a1, a2, this vector must also be a1, a2. How about this? So is this. How about that? So is that. So all these vectors can be called as vectors a1, a2. But here is the idea. If they are located, if that vector is located over here, we may not be able to detect that it is actually a1, a2 readily. Well, in that case, just move this so that the tail falls on the origin. And then see where the arrow falls, what the coordinates of the arrow would be. That tells you what this vector is. That's one way. Okay? Or without moving and all that, could we still be able to tell what this vector is? Here is the idea. For instance, let's say we have the tail is at 3, 1 and head is at 6, 5. Can we figure out the components of this? That's the beauty of this one. Given points, even though I'm showing you two-dimensional things, we can extend this to even three-dimensional points. If point P has x1, y1, z1 as its coordinates, and Q has x2, y2, z2 as its coordinates, then the vector going from P to Q, let's say vector A, that goes from P to Q, is simply given by A is x2 minus x1, comma y2 minus y1, comma z2 minus z1. So those are the three different components, the x component, the y component, and the z component of this vector A. So could we tell what this vector is? Well, we wouldn't have a z component, but not a big deal. It has x and y components. So 6 minus 3 is 3. 5 minus 1 is 4. So 3 comma 4 is this vector. Angle bracket 3 comma 4. Now if we were to scoot this so that the tail falls on 0, you'll be guaranteed that the head would be at 3, 4. Okay? All right. And if P happens to be the origin, then we call the Q as the position vector. In this case, the PQ. We won't say PQ because P happens to be the origin. We'll simply call it vector Q. And it's called the position vector. Anytime the tail of the vector happens to be at the origin, we call that vector as the position vector. Cool? All right. What are the advantages? Why should we learn to do this component representation? There are advantages. For example, given a vector a1, a2, a3, the x component is a1, y component is a2, and z component is a3, then we can immediately figure out what the magnitude of that vector is. That means the length of that vector. How? Simply take the square root of a1 square plus a2 square plus a3 square, and that's it. And uh, and also adding vectors becomes so much simpler. Earlier we saw the graphical method. You had to use the triangle method or the parallelogram method, draw, and all kinds. But if you already know the vectors in component form, we simply add the components. For example, a plus b, if a is given by a1, a2, a3 and b is given by b1, b2, b3, a plus b is simply this vector plus this vector is nothing but take the x component here and take the x component of the second one, add them up. That becomes the x component of the sum. a1 plus b1, a2 plus b2, a3 plus b3. Cool? I'll solve a few problems, I think, based on this. Uh, Next, one more concept. Unit vectors and standard basis vectors. There's something called unit vector. What's the definition of a unit vector? A vector whose magnitude is equal to 1 is called a unit vector. Okay, as simple as that. If you see a vector whose length happens to be 1 unit, you'll say that's a unit vector. Okay, and in physics, typically you see this I. What is this I? Component notation. That's just nothing but its magnitude along x direction is 1 and its magnitude in the y and z directions is just 0. So this I vector lies entirely on the x-axis and has a magnitude of 1. Similarly, the j vector lies entirely on the y-axis, or parallel to the y-axis I should say. And the x and y components, x and z components are 0. And k points in the z direction, positive z direction. And they are called the standard basis vectors. Okay, unit vector, standard basis vectors. We need to know them. And when we have A, as in the component form A1, A2, A3, it's perfectly possible for us to write this as A1 times 100 plus A2 times 010 and so on. So basically this is exactly the same as saying A1I plus A2J plus A3K. Right? Whether we write in angle brackets A1, A2, A3 or we say A1I plus A2J plus A3K, they are exactly the same. That we will be using quite a bit. Oftentimes we will switch from this notation to that notation and back and forth and all that stuff, depending on the problem. All right, next, properties of vectors. If A, B, and C are vectors in V sub n, whoa, what in the world is V sub n? Well, that's called a fancy word, vector space. So if we have an n-dimensional vector space in which A, B, and C are the vectors, in our case, we don't go beyond 3. So either a V2 or V3 is what we are always looking at. A 2-dimensional vector or a 3-dimensional vector. And C and D are scalars. That means real numbers. Then there are about 7 or 8 properties. 7 properties, I think. Addition of vectors is commutative. Ooh, Fancy word, commutative. Commutative simply means a plus b is equal to b plus a. Commutativity of addition means. Um, and this property, a plus the quantity b plus c, is the same as the quantity a plus b plus c. Anybody? Any idea what this property is called? Associative property. Okay. If you associate b and c together first and then add a to it, or you add a and b, associate them first and then add c to it, you will get exactly the same thing. Okay. And then there is something called zero vector. Here I was careful to write 0 as a zero vector. A vector plus a zero vector is always equal to that same vector, right? And this is 0 is called the additive identity. Additive identity. And if you add a and a vector negative a, what is negative a? Has the same magnitude as a, but the direction is opposite. You get the zero vector. So negative a is what is called as the additive inverse of a, or a and negative a are additive inverses of each other. Okay. The next property, a scalar c times the vector a plus b, you can distribute ca plus cb. And if you have two scalars adding up and they are multiplying a, then you can do ca and add that to da. Okay. To me, these are fairly straightforward things. There's nothing big deal about it. And the seventh property is 1 times a. If the magnitude, the scalar is 1, and you use that scalar of 1 to multiply a, you'll get back a. Okay, that's fairly straightforward. Okay, finally, let's solve some problems. This may be a bit of insulting of your intelligence. They are all fairly straightforward in my opinion. A plus b. Can you figure out a plus b if a is 5i plus 3j and b is negative I minus 2j? Piece of cake, right? A plus b would be 5i thing. You need to take the x components, add them up, and add to that the sum of the y components. So 5i minus I plus 3j minus 2j. Cool? 5i minus I is 4i. 3j minus 2j, j. So basically 4i plus j. As simple as that. Cool. 4a plus 2b. 4 times the a vector plus 2 times the b vector. Multiply. You can distribute according to the properties of vectors. And then add the like components. 20i plus negative 2i is 18i. 12i plus negative 4j is 8j. Magnitude of a. Magnitude. Square root of 5 square plus 3 square. Okay. 25 plus... I'm an idiot. 25 plus 9. What was I thinking? I thought 3 square was 6 probably. I'm such an idiot. Sorry about that, guys. This should be 34. Square root of 34. Yeah, let's fix that. So 5 square plus 3 square, 25 plus 9. Yeah, 25 plus 9 is 34. Square root of 34. That's the magnitude of vector A. And what's the magnitude of A minus B? Well, to figure out the magnitude of A minus B, first go ahead and figure out what A minus B is. And in component notation, it's much easier to do the subtraction. 5i minus negative I is 6i. 3j minus negative 2j is 3j plus 2j, which is 5j. Now we can do the square root thing. Square root of 6 square plus 5 square. 36 plus 25. 41, 61. Yep. Hey, I did add that thing right. Uh, cool. What's the next problem? Find a plus b, 4a plus 2b, absolute magnitude of a minus b, blah, blah. Simple, right? We have in the component notation. So add the like components, multiply, blah, blah. Are you okay with me if I did this, folks? 8 square plus 1 square plus negative 4 square all under a square root. Does that really turn out to be 81? I lost my confidence in adding. 64 plus 1 is 65. 65 plus 16, 71, 81. Yep. Hey. Time to rejoice in doing the right arithmetic. 3, 3 and negative 5. Would you agree? 8 minus 5 is 3. 1 minus negative 2 is 3. Negative 4 minus 1 is negative 5. So the magnitude would be square root of 3 square plus 3 square plus negative 5 square. 9 plus 9 is 18. 18 plus 25. 43. Yep. Cool. That was pretty straightforward, right? Alright, let's move on. Find a unit vector that has the same direction as the vector A. Ooh. Unit vector. What's a unit vector? It's a vector that has a magnitude of 1. Oh, can we say I? I is a unit vector, right? It has a magnitude of 1. But, we cannot just simply say, they didn't say give me a unit vector. They said find a unit vector and put another restriction. It has to have the same direction as this vector A. How do we do that? We will need to do this quite a bit, so definitely pay attention to this if you do not happen to know this. You want to find a unit vector of A. You take that vector A and divide it by its magnitude. When you do that, the resulting vector is guaranteed to have a magnitude of 1. Any vector divided by its magnitude will give a vector whose magnitude would be 1. So, take this guy and divide that by the magnitude of this. And the magnitude of this is 25, 9 is 34, 34 plus 1 is 35, square root of 35. And so, can I do that? Yeah. If I have A plus B over C, can I write that as A over C plus B over C? Are you with me? Let me repeat that. If I have A plus B over C, all over C, can I write that as A over C plus B over C? Yep, that's exactly what I've done. Negative 5i over square root of 35, which we can write as negative 5 over square root of 35 times I, and 3 over square root of 35i, and so on. So this is a unit vector. You're not convinced? You should be, or check for yourself. Take this guy, square it, take 3 over square root of 35, square it, and negative 1 over square root of 35, square it, and add them up and take the square root. Well, the tops would be 5 square, 3 square, and 1 square, which will add up to 35, a square root of that. And in the bottom, you'll have a 35. So square root of 35 over 35 is what you would get. Obviously, that's equal to 1. But this is key though. You are given a vector. You want to find a unit vector along the same direction. Then this is what you do. You divide that vector by the magnitude of that vector. Cool. All right. Find the angle between the vector A and the positive direction of the x-axis. Ooh, some vector is pointing in some direction, right? Let's say it's going like that. We want to find out what its angle is with respect to the x-axis, positive x-axis. Well, how do we do that? Angle theta is found by recognizing tangent theta is equal to y component over x component. This is true only in case of two-dimensional vectors. Let me point that out. Tangent of the angle from the positive with respect to the positive x-axis, let me say that again. The angle between the vector and the positive x-axis is theta, and then tangent theta must be the y component of the vector over the x component. What's the y component of this vector? Square root of 3. And whatever j is being multiplied by, that's square root of 3. What's the x component? Whatever I is being multiplied by, which happens to be 1 in this case. So that's just square root of 3 over 1. Tangent theta is equal to square root of 3 over 1. Well, do we know if tangent theta is equal to square root of 3 over 1, what theta must be? Right? Recall, tangent theta is sine theta over cosine theta. So there is a certain theta for which sine theta is square root of 3 over 2 and cosine theta is 1 over 2, which is 60 degrees or pi third radian. So theta is pi third radian or 60 degrees. Cool. That's how you find in two-dimensional case the angle between the vector and the positive x-axis. While this is the way we find the angle in 2D case, the approach is different in 3D case, which we will learn in the next section on dot product. Okay, that's a promise. Okay, one more thing. If vector A lies in the first quadrant and makes an angle of pi 6 with the positive x-axis and magnitude of A is 3, write A in component form. Ooh, this is different kind of a question. We know the magnitude of the vector and we also know its angle with respect to the positive x-axis. So how do we find the x component? Well, since theta is pi 6, which is 30 degrees, x component is nothing but the magnitude times cosine theta. Okay, magnitude of the vector times cosine theta. So 3 cosine pi 6 is 3 times square root of 3 over 2. Cosine of pi 6 is cosine 30 degrees is square root of 3 over 2. And to find the y component, we do a magnitude of A times sine theta, and that's 3 times sine of pi 6. Sine of pi 6 is 1/2. So the vector A itself now in the component form is, we can write it as 3 square root of 3 over 2 I plus 1/2 j plus 3/2 j. Samuel. That should be 3. Sorry about that, guys. Save this. Let's go. 3 half j, cool, or 3 square root using angle brackets. Cool. So these are some simple problems. In homework, quite possibly I'll give you some things like that. And quite possibly this is the last one. Okay, yeah, especially as engineers and physics course taking people, you should love this problem. Find the magnitude and direction of the resultant force. Imagine there's a boat sitting in the center of a small canal or lake. From one side of from one bank of that thing, one guy is pulling the boat with a 20-pound force. On the other side, another guy is pulling this with a 16-pound force, and their angles are as given. Which way will the boat move? Well, the way you can find that is using vectors. You add these two vectors and you get the resultant, and as if, maybe, wait, what I mean by resultant, I'll explain in just a second. Let's go ahead and work the problem out. I hope I remember. Resultant is nothing but express this 20-pound force in component form. Can we do that? Yeah, we know its angle with respect to the positive x-axis as 45 degrees. So x component would be 20 times cosine of 45, and y component would be 20 times sine of 45, right? So 20 pound times cosine of 45 degrees I plus sine of 45 degrees j. That's the first vector. The other vector, similarly, 16 times cosine of what? Negative 30. What? Yeah. When it comes to measuring these angles, should we call them positive 45 or negative 45? It all depends on the direction from the positive x-axis. Pay attention to this, please. If we are measuring from the positive x-axis in a counterclockwise direction, that's considered positive. So to reach this vector 20 from positive x-axis, would you agree that we have to go in a counterclockwise direction? That's why this is positive 45. However, this 30 happens to be in a clockwise direction. So that's why it should be interpreted as negative 30 degrees. So plus 16 pound times cosine of negative 30 degrees I plus sine of negative 30 degrees j. Cool? 20 pounds square root of 2, cosine of 45 square root of 2 over 2, sine of 45 is also the same thing. Cosine of negative 30, yikes. Recall, cosine of negative theta is cosine theta. What is that? Cosine of negative theta is the same as cosine theta, positive cosine theta. However, sine of negative theta is negative sine theta. So we can replace this cosine of negative 30 with a cosine of positive 30. That's okay. And cosine of 30 is square root of 3 over 2. However, sine of negative 30 is negative sine of 30. Sine of 30 is 1/2, and so minus sine minus 1/2 j. Cool? And the rest is straightforward. Multiply them out, add the components. Yeah, I just left it like that. Cool? That's it, folks. So those are some of the concepts that you need to learn in this one, and please work on some homework problems on this, and you should be able to understand this section pretty easily. Alrighty, thank you.